Okay, we'll continue. So like, yeah, so there is like so much limitations with that. So right now, like in most of the like autonomous self-driving platforms, they use multiple sensors. It's much more safe, but on a production level, it might be very costly, like using lidars. Like if you take even if the like low cost three D lidars like Velodyne's lidars, they'll cost like 3 lakhs, 4 lakhs at least. Like if it is a 3D lidar. So to make some, a level 5 autonomous vehicle, you need all kind of sensors. You can't just use cameras. You can just use cameras. You need all kind of sensors, cameras, GPS, IMU, radar. So all these need to be interconnected, linked together to build the system. So so that's what we are generally going to see with ROS. So ROS I'm not going to say that like ROS is being used industrially on autonomous vehicles. It's not used industrially on autonomous vehicles. There is like this platform called AutoWare, which integrates ROS and which uses ROS as a background, a foundation for autonomous development. So that's still not used industrially, but there are like some very good development going in that direction. So in the future, robot operating system will be used in autonomous development. So why I'm talking about all these sensors and all these different things is because as we go on, we'll see why ROS is important when it comes to integrating multiple systems, multiple sensors and multiple systems into a single project. So it is a first piece truly driverless electric car prototype built by Google to test the next stage of its 5 years of self-driving car project. It looks like a cross between a smart car and a Nissan Micra. So like room enough for a small amount of luggage. It's the first real physical incarnation of Google's vision of what is self-driving cars near the future could be. How does it work? Powered by an electric motor, 100-mile range, and uses combination of sensors and software locate itself in the real world combined with the highly accurate digital maps. A GPS is used just like a satellite navigation system in most cars to get rough location of this car at which point radar, laser cameras take over to monitor. So the GPS is what actually guiding the car on a long range travel from point to point travel. The GPS is what the GPS or GNS system in general is what guiding the autonomous car. Then on the local base, there are like these sensors, radar, lidar, cameras, ultrasonic sensors, IMU. All these are combined to make judgments about what is happening. More than like it is the finding the goal or the finding the route is like using GPS these days is not that much of a hard, it's not that much of a big task because we all know we all use Google Maps. But like finding in a real scenario, judging what is happening, what's in front of you, and how to react to that. All that is what in a traffic system. That's what's more important than the long range traveling. So for that, we need all these local sensors. So software can recognize very important thing like it can recognize objects, people, cars, road marking signs. So one of the most important marking that you need to recognize is a lane. So it should always keep with the lane and also obey traffic rules. So traffic rules means there should be like clear signboards and it should be able to detect and deduce the what that traffic sign means. If there is a stop sign, the car should stop for stop and check for any other vehicle before taking the turn. So if there is a red light, it should slow down and stop at the red light, and it should move. And if it is on a highway, if it needs to take an exit, it should see the exit sign long time. There will be an exit sign like 100 or 200 or 300 meter before the exit itself. So it should detect that exit sign, and it should judge that in a little while an exit will come. So it will have to take that exit. So it should keep to the right lane or the left lane depending on the exit. So that all that things are included. All those things are done using like all these different sensors and cameras. So equipments used like LiDAR systems, video cameras, radar system, ultrasonic sensors, and there is a central computer. So it's not just a central computer. Like if even if you take the most basic cars these days, it comprises of like the if you take like AUTOSAR architecture, it comprises of a CAN network with so many ECUs that are interconnected, and each are like separated into different units. A single unit can contain multiple ECUs, and it can multiple ECUs, and it comprises of like it might be doing a single task in a single bigger task. So if you take even if you take a simple car like these days, a low-end car, still there'll be so many sensors and ECUs included. So if you take a self-driving car, that has to be multiplied like so many times. And definitely there will be a central processing unit that will be doing or multiple central processing units that will be doing the bulk of the sensor processing. So LiDAR sensor is designed for obstacle detection, navigation of autonomous ground vehicles. So it's a local sensor that is used for scanning the surroundings. So it can effectively scan the if you are using a 3D, there are multiple types of LiDARs are there. So if you start from basic level, there is TOF LiDAR, time of flight LiDAR, which can only see in line of sight. So it's like an ultrasonic sensor or some IR sensor. It can only like detect things in its line of sight. And then there is 2D LiDAR, which can only detect things in a plane. So we can use 2D LiDARs in small robots and things like that, which doesn't move in a very challenging environment. It just moves in like in indoor environment where we can use a 2D LiDAR. And then there is 3D LiDARs. So 3D LiDARs or multi-beam LiDARs. So multi-beam using multiple beams. Like it depending on the kind of LiDAR, the number of beams will differ. Number of beams will change. So using that type of LiDARs, we can scan the entire area, and we can use it for object detection. We can create an entire world, using these lidars, and we can see whether there are humans or whether there is a road or buildings, cars. Everything can be detected using these lidars. And 3D model of the immediate surrounding can be immediate immediate surrounding can be built. Then video cameras, different types. So there'll be cameras inside and outside the vehicle. There could be cameras inside and outside. Definitely, you'll have to monitor the people inside, and definitely more than that, you'll need to use cameras outside. So cameras can be used for like if you use lidars, you cannot do tasks like detecting a signboard because it signboards are very like color based. So you need to use object detection with with the basic object detection or segmentation or something like that, where you will definitely need a very good quality 2D camera. So cameras, multiple type of cameras, like whether it could be a 2D camera or it could be stereo camera, 3D camera. So multiple type of cameras should be used. Then radar system, radars are installed front and back. So radars are mostly just for like, so we know the principle of radar. Radars are used in like uh, aeroplanes and ships and places like that, where it is used for like detecting. It cannot like build an environment like a map like lidars can do. They can just detect things around it, but its range is higher than a lidar. Lidar's range is smaller than a radar. Radar can detect things farther from farther away, but they can only form like a very simple idea of whatever the object is. So we cannot use object like we cannot do object detection and things like that using radars. It's like simple obstacle detection, and it cannot we can judge the size of the object and things like that. So then it uses it you used to measure the position of object very close to the vehicle. So ultrasonic sensors, like very close, like if the vehicle, if it's too close, like in parking cases scenarios, if the car has to self park, then definitely if it is a very tight parking slot, or if it is parallel parking, some scenario like that, then you need some kind of precise sensor which can detect things very nearby. So that means multiple ultrasonic sensors need to be, attached all around the sensor. So this is like the Google self-driving car, where what are all these things, what are the different things it uses. So here, like all the whatever I've been just talking about, it all just comes together here in this slide. Information from all the sensors analyzed by central computer. It manipulates the steering, acceleration, and brakes. So it uses like a drive-by-wire system. So it's called a drive-by-wire system because like in manual case, we use pedals to accelerate, and if it is a manual drive car, then you'll have to use a stick to shift gears, and you'll have to steer with your hand. But in a drive-by-wire system, or in a drive-by-wire, steer-by-wire, brake-by-wire system, everything is done by giving pulses through wires. So like steering is controlled by giving you know is steering is controlled automatically, the acceleration is controlled automatically, braking is controlled automatically, everything is controlled by giving small electrical pulses. So key factors about the vehicle sensors and hardware components that have been custom built for the self-driving. New technologies to protect pedestrians, including flexible windscreen, front-made foam-like material, an electric battery, speed capped at 25 mph, primary backup system for steering and braking, and software designed to drive the point to point without requiring human intervention, seats for two passengers, and space to belong, like all this about the specific car itself. So like all the sensors and things that we've been talking about, the laser 360 degrees around the vehicle for object detection. So this is a lidar sensor, and the processor regulates vehicle behavior. Processor and wheel hub sensors detects number of rotations. So each and every wheel will have individual sensors. So even if they might have like different rotation RPMs. So you need to actually measure the RPM of each and every wheel individually and take an average of that. radar measurement speed of the vehicle ahead. Like, yeah, radar is used for like measuring the speed of the vehicle. And an orientation sensor tracks the motion balance, like an IMU system can be used for that. So advantages: managing traffic flow, relieving vehicle, avoid accidents, increase like all these like determining current location. So then recent developments expanded. So Wyoming, this system is called Waymo. So expanded testing Waymo 1 to San Francisco in 21, 22, like in March 22, Waymo said they will begin offering rides in San Francisco without drivers. So then Uber has its own autonomous vehicle prototype testing in San Francisco. So these are like different links you can use. This is the link like you can use here for reference. Then we will go into the specific topic that of today, that is robot operating system. So what is robot operating system? So robot operating system is a open source robotic middleware suite. It's called an operating system, but it is not an actual operating system. It's called a middleware suite. So you need to already have a operating system installed. So if you take from a practical point of view, it is always better to use Ubuntu and install that in some system. So if you want to make a robot or an autonomous vehicle, it is always better to use a portable mini computer. So we need definitely we need to process a lot of graphical data. So that means GPU is important. So when it comes to GPU, it's better to use NVIDIA processors. So we have like this, there is this line of NVIDIA boards, different type of NVIDIA boards like Orin, Xavier. We can use some kind of board like that, and we can install Ubuntu operating system. And on top of Ubuntu operating system, you can install the robot operating system. So there is two versions in ROS 1 and ROS 2. We will be mostly discussing ROS 1 here. There is like on the surface level, ROS 1 and ROS 2, like if you're a developer, if you're writing software for ROS robot operating system, then it's not much of a difference for you. There is not a big difference between ROS 1 and ROS 2. There are like some differences, like you can write like launch files using Python in ROS 2, things like that. But there is no major differences. But in but when it comes to what is underlying the core features, we'll discuss all that. We'll discuss all that as we go. So underlying features will differ, like security and communication. All those things will differ in those two. So it's although ROS is not an operating system, but a collection of software frameworks. It's a collection of software frameworks for robot software development. It provides services designed for a heterogeneous computer cluster. So it's for a heterogeneous computer cluster. The computer, it doesn't need to be installed. The operating system doesn't need to be contained into a single computer. It doesn't like it could be clustered around, like could be a cluster of heterogeneous computers. There could be a microcontroller, there could be a single board computer, and there could be a PC, and all these three things could work together to make a single system work, make a single robot or an autonomous car work. So that is the advantage of using ROS. We can interconnect all these different computer systems to make a single system. So then other thing is hardware abstraction, low-level device control, implementation of commonly used functionalities, message passing between processors and package management. So we'll go into all these in details. So hardware abstraction and low-level. So what is hardware abstraction and low-level device control? So what is hardware abstraction? Are a set of routines in software that provides programs to act with access to hardware resources to programming interfaces. The programming interfaces allows all devices, in particular Class C hardware devices, to be accessed through identical interfaces, even though C may contain different subclasses of devices that provide a different hardware interface. So it's like a hardware abstraction means like we know about like drivers. So to use some kind of so when you connect an external device to your system, a printer or something like that, you'll definitely need to install a driver on your system, or automatically that driver will be installed. So the whatever software that you are using in your system, Adobe or whatever software that you are using in your system to print, it doesn't need to like know the underlying communication between the printer and the computer. If the uh, driver is there, acts like an interface between, so between the person who writes the software or for this particular this software interface for the printer. They don't need to know about the underlying hardware, what is the hardware, how the hardware communication is working. They don't need to know all that, because so that is in a nutshell, that's what hardware abstraction means. So they're like softwares that provide access to hardware resources through programming interfaces. So then plumbing means like message passing, publishing, subscribing, message infrastructure. Then ROS provides an extensive set of tools for configuring, starting, introspecting, debugging, visualizing, logging, testing, stopping, distributed computer systems. Capabilities, ROS provides a broad collection of libraries that implement usual robot functionality. So like things you need, definitely when you're developing something, you'll need to be, you need to debug things, you need to visualize things, you need to log the data, whether for error checking or whatever it is, and for testing you need purpose, you need to simulate things. So ROS provides separate tools for all these. You can either when you install it, will come with the whole thing, or you can individually install all these things. So we'll see what are these things individually. Capabilities, ROS provides a broad collection of libraries that implement useful robot functionalities with a focus on mobility, manipulation, and perception. So like for example, pathfinding. In pathfinding, there is like this algorithm called RTB or Digistra. These type of algorithms, you don't need to implement these algorithms from scratch. In case of ROS, you can just call a function. You can just configure a node and activate the node. So automatically this will work. Ecosystem was supported improved by large community with a strong focus on integration and documentation. So then hardware, so key features are like hardware abstraction, low-level device control, programming language independent, implementation of wide range of commonly used tools and algorithms, message passing between processes, OS independent, standardized package management, useful set of shell commands and utilizes with tab completion. So then we'll just go into more in depth into ROS. So like I said, we've been just saying ROS continuously, and I've been talking about different things like features of ROS. So now we'll see what is actually ROS. It actually means. So if you take ROS one, there is a ROS master, and there are nodes. So a node is a basic process that operates process that performs computation in ROS ecosystem. Key points: each node has a unique name. Nodes can communicate with each other using topic services and actions. So then, modular design, each sensor, actuator, algorithm can run in a separate node. So that's what a node means. Each node has a unique name. First of all, it needs to have a unique name, and it can be anything. A node doesn't mean a particular thing. It can be a hardware, can be a sensor, or it can be an actuator. It can be an algorithm running like a RTB or Digistra or some kind of algorithm running. Could be some software algorithm running. So a node can be anything. It doesn't need to be a particular thing. It doesn't need to be a hardware or software. It doesn't need to be. It can be anything. So it could be a GPS, or it could be lidar. The lidar is actually we've discussed in in the autonomous, the Google car. There is lidar. So the lidar is a node. in ROS case, when it comes to ROS, LiDAR is a node, and the GPS is a node, IMU is a node, wheel encoders are nodes, and then there is a local planners, global planners, uh, and then there are like other things like DWD. So this like localization, AMCL, like advanced like Monte Carlo localization, that type of software systems. So Node can be any of these things. So it is a collection of all these hardware and software, all these things that need to be connected. Here you can see what ROS does is it doesn't like it doesn't provide a an interface, separate interfaces for like hardwares and softwares, everything get a general name and a node, and how the communication happens between these two, whether it is a software or a hardware. Obviously, when it is a software, when it is a hardware, obviously the hardware to interface with the whatever computer device you're using, there will be a driver, some kind of driver software. So that driver software will communicate with the other parts, other softwares. So it doesn't treat like software or hardware or different kind of hardware or different kind of software differently. They all get the same kind of treatment, and they all communicates the same way. So that's another thing about and then modular design, and it's modular. Each thing can have its own, like a LiDAR works totally different from a radar or a software node that's running. So they're all very modular. And so examples of nodes are like LiDAR node for scanning, navigation node for path planning, like GPS or GNSS system in general. So in ROS 1, there is a ROS master. So that is one of the difference between ROS 1 and ROS 2. There is no master in case of ROS 2. But in ROS 1, there is a master. And the master starts initially, and every other node starts afterwards. So then what are topics? Topics are used for asynchronous publish and subscribe communication nodes. So for example, so I'll share the attendance link right now. You can just use the attendance link. So yeah, the topics. So topics are just like so I just shared the attendance link. You can just log in and fill the form. Just share the attendance form in chat. You can just log in and share it along, fill the form. So topics are used for, like, they use this technique, publish subscribe communication. It's an asynchronous communication. So there is no like what is difference between asynchronous synchronous. Synchronous means there will be a clock synchronizing. There will be some timing function that synchronizes the communication. But in asynchronous communication, there is no such thing. Data will be sent continuously, and even if there is no receiver, the data will be sent. So here it's called publish and subscribe. So there is a publisher node and a subscriber node. So publisher node sends messages to a topic, and the receiver and the subscriber node receives the message from a topic. So Advantage of using a topic and this type of communication is that multiple receiver nodes can receive data from a single node. Like for example, a lidar data. We're taking the lidar data. At the same time, two software nodes need to get the lidar laser scans. So that can be done using this type of communication. The LiDAR node will publish the data, push the data using the publishing technique, using a topic like standard topic like laser or something like that. So laser scan under like slash scan or slash laser can use some kind of topic like that. So any node that needs to get that data, that LiDAR data, it can subscribe to this particular topic and it can read that data. So there is no need to establish communication between these two nodes. In that case, any node can get the data. So predefined data structure. So the data structure is predefined. Like in any asynchronous communication case, the data structure is predefined. The messages are predefined. So both nodes knows how to read and how to decode the data. So example of like rows topic is like topic list. You can just use this command rows topic list to print all the different active topics. OS topic echo scan means it'll print. So if you run this in Bash, if you run this in a Bash terminal, it'll print all the scan values, all the laser values. So laser cloud, point cloud data, all that data will be printed on the terminal. Then CMD, like different use cases like command velocity. So one most important thing is like in the case of like the Google car, definitely there need to be a command velocity sent to it's an electric vehicle, so a command velocity need to be sent. The velocity will be converted to some other kind of way, like whether they might be using PWM or FOC or some kind of technique to. They might be using a PWM or some kind of technique to control the speed of the motor. So that pulse that need to be that that conversion need to be done, but from rows what we'll get is command velocities in like meter per. So everything is in standard units, everything is in meters, everything is in seconds. There is no kilometer, there is no microsecond, millisecond, everything is in meters and seconds. And so we'll get the command velocity in meter per second. So and if it is angular velocity, we'll get the angular velocity. So we'll get both these things. So it will be with the topic name command velocity. So any node that need to access this data, they can subscribe to this topic and they can use it. So then ROS services. Services are used for synchronous request response interaction between nodes. So it's synchronous, unlike topic communication. It's a synchronous communication. So it is established between two nodes that know they are communicating with each other. So there is a request and reply. So ROS master takes care of all this. So both has to register with the ROS master service. There is a service server and there is a service client. So services are mostly used for like things like computations. So there is like a service server which does some kind of mathematical computation with some data, incoming data, and that will be sent to the service client upon request. So structure, service, request plus response are defined in SRV files like standard SRV, STD SRV or set pool. Example, you can just use these commands like rows service list, low service call, robot STD, different things like that. Use cases, resetting the sensors. So it can be used for resetting the sensor. So resetting the sensor, changing robot mode, querying sensor data on demand. So this type of things can be used in services. So it only need to be done when particular command is sent, like a particular request is sent. So it's a synchronous communication. It's a synchronous interaction between nodes. So this is like the basic difference between ROS 1 and ROS 2 that I've been talking about. On the outer layer, as a programmer, there is not much difference. It's almost all the same. But if you go under the hood, then you'll see like this type of differences, like architecture, single master. In case of ROS 2 is distributed with DDS system. DDS is a protocol, and real-time support limited, real-time safe with the DDS. Security, no built-in security system, supports encryption authentication with the DDS. Communication, custom TCP, UDP, ROS, TCP, ROA, ROS, TCP, ROS, DDS-based pub sub transport. OS support most Linux, cross-platform like Linux, Windows, Mac OS. Mostly in ROS 1 is just mostly Linux. Scalability very limited, better suited for embedded and large systems. Ecosystems mature, stable, rapidly evolving with the modern tools. So that's it. That's it for today. We are not going into any practical things today. So I'll have to wind up the session for today. So tomorrow we'll see more, practical things in deep learning, and I'll I'll be able to show you some demo on robot operating system, not an actual live demo. I've already we already have a autonomous robot which we have already developed. So I'll show you the videos and I'll explain everything working and everything tomorrow. So I hope the session was helpful. So tomorrow we'll see you again. Thank you.